Let's talk about the effective potential in the orbit, which is the potential considering the centrifugal force. Consider the energy and the angular momentum. So the energy is equal to the kinetic energy plus the potential energy, and the angular momentum is r squared phi dot. You identify the angular momentum with the azimuthal velocity. So substituting the angular momentum into the energy, the square of azimuthal velocity is the square of the angular momentum over r squared. So you can write the energy as, and if you group the angular momentum with the potential energy, now you can write these two terms as an effective potential. So that the energy is the kinetic energy, which is this term, minus an effective potential. And the effective potential is the angular momentum, and the effective potential is a function of the angular momentum minus the potential energy. Now this term in the potential is repulsive, and it's of course due to the centrifugal force. Now you can write this potential in terms of quantities A and B, write it as A over r squared minus B over r. And this potential is sketched here in this figure for A equal to 1 and B equal to 2. You can see here A is equal to L over L squared over 2 and B equal to mu. So the A term is the centrifugal barrier. It's only the positive part. That's this one here. There's a dashed line. It impedes the object from getting too close to the center. The second term is the potential well. It's the blue curve. Now the effective potential is the black solid line. If r tends to 0, the centrifugal barrier dominates, and if r tends to infinity, then the potential term dominates. As you see here, the effective potential has a well-defined minimum. The very minimum of energy allows for only one possible value of r, which corresponds to the circular orbit. So if you are at the minimum state of energy, this is the only radius that is allowed. As the energy increases, say that you are now at this level of energy, then a range of radii become allowed. You can go from this radius all the way to this radius, and that corresponds to elliptical orbits. Now, as long as the energy is negative, the orbit is closed, limited between these extrema. And as you see, these extrema are the perihelion and the aphelion. The semi-major axis increases with minus b over 2a. So that gives you here where the semi-major axis is for the elliptical orbits. As the energy approaches 0, the semi-major axis approaches infinity, and so does the apoastron. When the energy is positive, then the orbiter is able to reach infinity with either 0 velocity, that's the parabolic orbit, or non-zero velocity, corresponding to a hyperbolic orbit. So these orbits would be unbound. While planetary orbits are usually very close to circular, cometary orbits tend to be very elliptical. This is the orbit of Halley comet. The eccentricity of Halley's orbit is 0.967. It's very elliptical. You see, the perihelion is inside the orbit of the Earth, and the aphelion is beyond the orbit of Neptune. It's the study of the orbit of comets, actually, that made us realize that there exists something like the Oort cloud. The Oort cloud of comets surrounding the sun. If you have a significant number of comets, you can start tracing their orbits and see if you find any clustering. So this is the semi-major axis distribution seen from the orbits of comets. You see that there are two clusters, right? You have the cluster of the short period comets, peaking at about 7 years, and then beyond that, the long period comets. The long period comets have a clear peak at semi-major axis infinity at 1 over a, which is what's being plotted here, equal to 0. And when you look at their eccentricities, they're very close. This peak here, the peak of the long period comets, it's very close to 1, so 0.99 eccentricity. That means that a majority of comets have parabolic orbits, infinite, semi-major axis, and eccentricity equal to 1. If they have parabolic orbits, they're very weakly bound. Their energy is very close to 0. And when you look at the other orbital parameters, the inclination, the longitude of the ascending node, and the argument of perihelion, they're uniform. So the fact that the inclination seems to be uniform means that their orbits are pretty much randomized in inclination. They are at a sphere around the sun. So that is the interpretation of these orbital elements. A sphere of comets around the sun. With the semi-major axis being infinite means that they are weakly bound. They go all the way to when they are very weakly bound to the sun, almost half of the way to the next star. That's when the gravity of the galaxy starts to play a role, and you cannot ignore the tides anymore. And the tides of the galaxy are enough to ionize the cometary orbit away from the sun.